This is exercise 4. This is exercise 4? Yes. Exercise 4. And this is an extension of the exercise 3, but this is to take care of the case where the exponent is negative. So, and I have a number n that is 10 to the raised to some negative exponent with characteristic and mantissa terms. How do we handle that? How do we make the conversion between this number and either the scientific notation or from scientific notation to the exponential form? And it turns out that if the exponent is negative, then the log of p, precision term, is going to be 1 minus the 0 point m term, the mantissa. And that there's going to be another number q, which is going to be equal to the characteristic term plus 1. And so then the number itself in scientific notation is going to be equal to p, be factored into a precision term, times 10 to the minus q. And only the q part is negative. The p term is always going to be positive. That is the convention with scientific notation. So we have to bring it to somewhere this is some positive number, and the only negative exponential term is in the characteristic part, and that is going to be the q term. So what this exercise is, by just an extension, knowing when to add and when to multiply, is we take the raw number n, and we're going to re-express it in this fashion. So I have 10 to the minus c dot m, and that's going to be equal to 10 to the 1 minus 0 point n times 10 to the minus c plus 1. And then I end up with the scientific notation. I have the precision term times 10 to the minus q term, which is the only negative part. And this is a simple, a slight variation on what we've been doing all along. And for example, if n is equal to 10 to the minus 5.301, then the log p part is going to be, I take the mantissa and subtract it from 1, and 1 minus 0.301 is 0.699. And the q term is going to be the characteristic 5 plus 1, and that's equal to 6. So that means this number 10 to the minus 5.301 is equal to 10 to the 1 minus 0.301 times 10 to the minus 5 plus 1, which is 10 to the 0.699 times 10 to the minus 6. So my characteristic term, my scaling factor here is the minus 6. And this we recognize. This is equal to log of p. The log of p, therefore, 0.699 is the log of 5.00, which has the precision, 3 significant figure precision. And this is my scaling factor, 10 to the minus 6. So this is just what we need to practice, going back and forth between the scientific notation and the exponential form, or the exponential form and the scientific notation. And this with a little practice comes routine. So the first exercise, again, what is the log of the following number? 10 to the minus 4.77. Well, this is going to be, going this way is really a lot easier, actually. This is going to be equal to, this is, then the p, or log of p, or should I say, the log of p is going to be equal to 1.0 minus 0.477, and that is equal to 1 minus 0.477. Now, I figure that would be a 3. This would be a 2, and then 9 minus 4 is 5.0 0.523. Okay, and now the characteristic term, a Q, is equal to Q is equal to 5 plus 1 equals 6. And therefore, I have to now determine what this P is log of, well, let's write the number out. 10 to the minus 5.477 is equal to 10 to the 0.523 times 10 to the minus 6. And now the problem here is 0.523. Well, within our logs, we know that, for example, 10 to the 0.477 is 3. And 10 to the 0.602 is 4. So it's between 477 and 602. So our first guess is between 3 and 4. So I'm going to start looking around 3.5. And it depends on how much time I want to spend on this, but I'm going to start over on my scratch paper, and I want to find what this is. And between 3.5 and I'll do as a starting point. Well, 3.5 is 5 times 7 times 10 to the minus 1. So I'm going to take the log of 5 and the log of 7 and add them together and subtract 1 from the result. So, because this is 5 times 7 times 10 to the minus 1. Now, this is 0.699, and this is 0.845, and 9 and 5 is 14. Okay, that is 14. 8 and 7 is 15. 1.544. 1.544 minus 1 is equal to 0.544. So 3.5, the log of that is 0.544. Oh, that looks about 523 is a little less than 3.5. So it's not quite that big. We can go back down the other way to 3.2. 3.2. Let's try 3.2, which is 8 times 4 times 10 to the minus 1 is 3.2. 8 is 0.903. 4 is 0.602. 3 and 2 is 5. 0, 9 and 6 is 5. Okay, 1 by that minus 1 is equal to 0.505. So, damn. So it's not 3.2. That's too small. 3.5 is too big. So 3.2, there's 3.3 and 3.4. So I'll go with 3.4 and call it a day. So this is equal, because I don't want to spend too much time on it, to 3.40 times 10 to the minus 6. Okay, so in other words, we're not going to spend that much time on it. If I wanted to know, I could continue in this process and interpolate in such a fashion to find. This is all my scratch paper work. But on a test, if I start giving you problems where you have to go that far, you can stop and approximate, and 3.5 would have been an acceptable answer. Would have been my first guess, my most immediately available. But recognize that we're losing a little bit on the precision here. So that's all you have to do. Now, for problem B, I have 2.0 times 10 to the minus 4th. We're going to catch a break on this one because this is going to be, we're going, I'm sorry, the log, boy am I stupid, what is the log of this? The log of 10 to the minus 5.477 and the log of 10 to the minus 5.477 is equal to minus 5.477. So I'm an idiot. I just went through a lot of work on the types of problems we're going to be doing next by not recognizing that the question was, what is the log of 10 to the minus 5.477? Now we can get to the other problems. And I'm going to erase this. Or should I erase that? Yeah. I'm going to erase that, and we'll do this one. Now, this is actually much easier, going this way. Okay. 2 is equal to what? 10 to the 0.301. 10 to the minus 4 is 10 to the minus 4. What do I do with that? I add. When I multiply two numbers, I add these together. That's minus 4.301 equals minus 4 plus this is equal to 10 to the minus 3.699. Okay? And so then that, the log of 10 minus 3.699 is equal to 3, minus 3.699. Okay. Now we're on a roll. Now I have 1.2 times 10 to the minus 7th. Okay. I'm going to have to find is equal to, we've already found the log of 1.2 in the previous problem. So that's equal to 10 to the 0.079 times 10 to the minus 7. And all I have to do now is add. I'm going to go over my scratch paper. And minus 7.000 plus 0.079 is, okay, that's a 1, that's a 9, which is a 2, and this is a 9, equals minus 6.921, equals 10 to the minus 6.921, and the log of 10 to the minus 6.921 is equal to minus 6.921. And so we're not quite done after that great digression. Convert the given exponential numbers into scientific notation. This is the problem I was working on before. Okay. That is something we have to convert to scientific notation. So that means I have to recognize that log, because this is a negative number, log p is going to be equal to 1.0 minus 0.301, and that's equal to 0.699. Okay, and the Q term is equal to the 2 plus 1, C plus 1, which is equal to 3. And therefore, the number n, 10 to the minus 2.301 is equal to, the log of p is 0.699. Well, let's just go ahead and put that. 10 to the 0.699 times 10 to the minus 3. And then we recognize this as 5. 10 to the 0.699. So it's 5.00 times 10 to the minus 3. And again, we've got 3-point precision here. We've got 3-point precision here. And so actually going this way is a little bit easier. And I actually sort of cheated and chose a couple of easy examples here that are going to work out nicely. Though we saw what happened with the previous one where we had to make approximations. So this one, 10 to the minus 5.699 is such that log p is equal to 1 minus minus 0.699, which just turns out to be 0.301. That's what I mean when I said I cheated and made it easy. And Q is equal to 5 plus 1 equals 6. And 10 to the minus 5.699 is equal to 10 to the 0.301 times 10 to the minus 6. And then we recognize this as 2.00 times 10 to the minus 6. And that